All right, welcome back to the last video here for problem solving, chapter 7 and 8. So let's look at chapter 8, problem number 30. You have three cars, car A, car B, car C, and they're going along a road, so they go like this. One of them is at the flat side of the road, one of them is on a dip, and the other one is on a hill, going over something. Notice the radius of curvature here is like part of a circle of radius 200 meters, the same thing as part of a circle that's 200 meters. This one is horizontal, it's not part of a circle, just motion in a straight line. Each car is moving at 25 meters per second. Now suddenly, all cars, suppose they hit the brakes so hard that the brakes lock and the cars start to skid. So they start to skid, and when they start to skid, the brakes are locked, so it's friction, it's kinetic friction, because there is relative motion between two surfaces, namely the ground and the wheel and the tires. So they say take the coefficient of kinetic friction to be 1, and then they say what's the tangential acceleration for each. Well, let's look at car 1 first, car A. Car A, what are the forces on it? Well, there is the normal force, there is the mg. If you want, you can call it mag. And then since it's skidding, it's moving to the right and skidding, so there is the force of kinetic friction. By the way, let's call this is my x direction. And that's the y direction. So for car A, the net force in the y direction is equal to 0. The net force in the y direction equals to 0 because it's only moving in the x direction. There is no motion in the y, so that's 0. So I conclude that the normal force minus mg equal to 0. That means the normal force is just equal to mg, and therefore the force of kinetic friction is equal to mu k times the normal force, which is equal to mg. Mu k times mg. All right, and that's the force of friction. And now we know that the net force in the x direction is equal to the mass times the acceleration in the x direction. The net force in the x direction is the force of kinetic friction, and it's this way, so that's negative. So negative mu k times m times g equals to the mass times the acceleration in the x direction for car A. The mass cancels. In case you were wondering, you might say the mass, they didn't give us the mass, but it didn't matter. It cancels anyways. And so let me raise this up a little bit. And so I get the fact that the acceleration in here is simply equal to minus mu k times gravity. And so that's equal to minus, mu k is 1 times 9.8, so it's just negative 9.8 meters per second squared. So that's the tangential acceleration for this one, along the x direction. For the other car, for this one, for car B, let's look at car B. We use red. What are the forces involved? Well, there is it's in contact with the ground, so there is normal force. There is mg. What else? It's skidding, so there is the force of kinetic friction. And so for this card, this is the radial direction, and this is the x direction. So here is the radial direction, and this is the tangential. We call it let me stick with the same notation, the tangential direction. And then the z direction is out. So let's check out the net force in the radial direction first. So for card B, I got the net force on card B in the radial direction will equal to the mass times the acceleration in the radial direction. What are the forces in the radial direction? There is the normal force along the radial direction, so that's the normal force, minus mg because it's in the downward direction, it's in the negative radial direction. And that has to equal to the mass times acceleration in the radial direction. So the mass times the acceleration in the radial direction, that's v squared over r. And the acceleration is, the radial direction is this way, so that's positive. So that's okay, yeah. And so we get that the normal force, therefore, will equal to, you move the mg to the other side, so it would be, and factor the mass, so it would be the mass times g plus v squared divided by r. That's the normal force. That means the force of kinetic friction, which is equal to mu k times the normal force, so that's mu k times the normal force, which is m times g plus v squared over r. Okay, that's my force of friction. And then we'll say, all right, the net force in the tangential direction will equal to the mass times the acceleration in the tangential direction. Okay, so I have, on the right side, it's the mass times the acceleration in the tangential direction. Mass times acceleration in the tangential direction. What is the force in the tangential direction? There is only one, it's the force of friction. And if the tangential direction is this way, the force of friction, I'm assuming it's to the left. Because it's skidding to the right, friction will be to the left. And so it will be negative this magnitude of mu k. So it's this value there. Negative, okay, negative mu k m times g plus v squared over r, and again the mass simply cancels, and you get the tangential acceleration. A tangential will be negative mu k times g plus v squared over r, so it will be negative, mu k is 1, and then g is 9.8 plus v squared over r. They are moving at what speed? 25. 25, so v squared divided by r. R is 200 meters, so 200. And so that we need a calculator to probably do this. So let me get my calculator here. So I have 9.8 plus 25 to the power 2 divided by 200. So that's 12.925, 12.9 with a minus 9. So negative 12.9 meters per second squared. Let me make sure I have the right answer. I don't want to make a mistake. Can keep it till the very end. And that looks correct. Okay, good. Let me go to C now. Let me use a different color. Use green. Okay. So what are the forces on C? Well, it's on top of the hill, so there is a normal force. There is an mg as usual, downward. And what else? It's skidding, so there's a force of friction. What else? Nothing. So it's moving this way. And so, in fact, we usually choose the tangential direction to be the, you see this one is moving in a circle in the counterclockwise. See, our circle is counterclockwise. So the tangential direction for this one is actually this way, if you like. And then the radial direction is toward the center. That's the radial direction. With the radial direction. Okay, so we will say the net force in the radial direction will equal to the mass times the acceleration in the radial direction. What are the forces? You got the normal force upward, that's negative of the radial direction, so that will give me, let me do it here, negative n. And then mg is along the radial direction, so it's positive mg. And that has to equal to the mass times acceleration. The acceleration is in the radial, I'm sorry, not the radial direction, I'm sorry. Toward the center of the circle, I should say, in this r. Anyways, I misspoke. So we have times mv squared over r, acceleration. Squared over r. Move n this way and move this one this way, so you will get that the normal force will equal to mg minus mv squared over r, and so you get the normal force will equal to m mg minus v squared divided by r. means, let's write it here, the force of friction is the coefficient of friction times the nodal force, so that's mu k times m times g minus v squared divided by r. Yeah, that's the magnitude of the force of friction. Okay, so we will go now to the net force along the tangential direction, will equal to the mass times the acceleration along the tangential direction. What is the force? Well, we have the force of friction, and it's along the tangential direction, so we'll put positive there. So it would be mu k m times g minus v squared over r. That's the force of friction. That's it. That's the only force along the tangent, equal to the mass times the acceleration in the tangential direction. The mass cancels, and so the acceleration in the tangential direction will be mu k times g minus v squared divided by r, and mu k is 1, g is 9.8, minus v squared over r, that's 25 squared divided by r, that's 200. Times 200. The radius is 200 of the circle. And so we get 9.8 minus 25 to the power 2. Let's see, 25 squared over 200. I get 6.68 meters per second squared. Let me just double check that. Yeah, so it is 6.60. They have about 6.7. They approximate. Yeah, they rounded. All right, so that's okay, and we're good. And now to the last problem. Last, maybe, but not least. I mean, every problem is good in its own way. You learn something from it. So let's go to the next problem here. We come here. So we have a ball. My demo. A ball is tied to the end of a 50 centimeters long string. The center of the circle is 150 centimeters above the ground. So here is, they drew a picture for you. So let me draw that picture. So here is the circle. The ball is going around a circle. They're saying that the distance from here to here is 150 centimeters. That's 1.5 meters. 1.5 meters. And then the radius of the circle itself is 50 centimeters. So so this is 50 centimeters or 0.5 meters. What that means is, so the ball is going like this. So when the ball is here, it's moving this way, and so it has a height h of what? 1.5 plus 0.5. That's 2 meters. 2 meters. That's the height. Okay. So you're doing this to the ball, and you're swinging it slowly enough that it barely makes the circle. So it barely makes the. I mean, if it doesn't have any speed, it will just fall on your hand like this. But you're swinging it barely enough that there is tension. So the tension is almost like loose. It's almost zero, as close to zero as you like. Let's say 0.00001 newtons, very close to zero. So it's like this. You time it. You're going like this, all right? And it's almost falling. And then what do? So it has the minimum speed to make it to the top without the string going slack, right? So it goes to the top, but without the string just getting loose and falling on your hand. All right, and then it says, if the string is released at the instant the ball is at the top of the loop, how far to the right does the ball hit the ground? So you time it. When the ball is here, you let go of the string. So you let go of the string, you just let go. So the ball will continue and go like that and then fall to the ground. So it will do this. It will get here and then just fall, all right? It will fall. And the question is, how far will it be? Let me call this the x-axis. And so, before we worry about that, we first need to find the minimum speed to make it above. So let's look at the ball when it's at the top. When it's at the top, this is the circle here. So this is the radial, this is the R direction. R direction. What are the forces? The forces are, there could possibly be tension, and there is mg. Mg downward. That's it. And so we know that the net force in the R direction will equal to m v squared over r. Mass times the acceleration in the radial direction. So v squared over r. The forces are the tension, it's in the radial direction. And then the mg is also in the radial direction, so I'll just call it mg. And then you have here m v squared over r. You have that. Now, if it's barely making it, the tension is really, really close to zero. So if it is barely making it, the tension is really close to zero, approximately zero at the top. So let's see what that gives us. So that means mg, this part drops, tension is non-existent then at the top, basically zero. There is a little bit of tension, but very close to zero. So I'm just going all the way to zero, as close to zero as you like. Or in the limit, the tension approaches zero. mv squared over r. So the mass cancels, and we get v will equal to just gr square root. Gr times the square root. That'll be v at the top. V. And it would be along this tangent direction, along the x direction. So let's calculate it. G is 9.8. R is, how much is it again? 50 centimeters for r, that's 0.5 square root. And we get, let me get rid of the mass here. Use my calculator instead. So 9.8 times 0.5 to the power of 1/2. I get 2.21. 2.21 meters per second. So at the very top here, it's 2.21 meters per second. Now you let go, you just have a projectile motion problem. You let go, the string is no longer there, you just have the only force acting then is the force of gravity, and it just goes like this. So here is the mass. It has an initial speed, is 2.2 meters per second. Let's draw something here. Here's the x-axis, here's the y-axis, and it's going to go like this. And the question is, what is x? Well, initially, y initial is the height of the ball. The ball is here. Again, we said this is 1.5, this is 0.5, so that's 2 meters. At the end, the ball hits the ground, so that's 0. The initial y velocity, the velocity is only in the x direction, so the Vy initial is 0. So we get y final equals to y initial plus Vy initial times the time minus 1/2 gt squared. I'm just using the motion at constant, motion, just free fall, motion at, with gravity only. Projectile motion. That's the one I wanted to say. The final place it falls is y equal to 0. Initially it's at y equal to 2. V initial in the y direction is 0. And then minus 1/2 of g, that's 9.8 times t squared. So the time it takes to fall will be, let's calculate it. Time it takes to fall will be what? 4 over 2 times, sorry, 2 over half of 9.8. And then to the power 1/2. I get 0.639. 0.639 seconds. That's how long it will take it to fall. And then in the x direction, there is no acceleration. It's just under the influence of gravity, under the force of gravity, which only acts down. There is no component this way. And so we get x is equal to x initial plus vx initial times the time plus 1/2 the acceleration in the x direction, but that's 0. There is no acceleration in the x direction. Initially, the x position, it was here, so that's 0. And then plus, the initial x velocity is the 2.21. And then the time is 0.639. And we get x, therefore will be multiply the 2 times 2.21. I get 1.41. Let me make sure that I have it correct. Yes, 1.41. No, not meters per second, just meters. All right, so that's all. And I hope you saw how I'm solving problems and how you approach them. Always set your coordinates. Look and apply Newton's laws. That's really it. If you, I don't know much more than you do in that regard. Just applying Newton's laws. Struggle with the problems. If you get stuck, that's fine. You can look at the solution or ask questions and then attempt it again on your own. It's healthy to struggle with it. This stuff doesn't come easy. At least didn't come easy to me. And I still struggle with it. I get stuck and make mistakes. That's fine. We all make mistakes. You just have to learn from the errors that you make. All right. I will see you next time.